No, this is fantastic. So,
hello, everybody. I'm very happy to have Martin Markl, a famous member of our institute, as a speaker of our seminar today. He should speak about his joint work with Denis Bashkirov on the combinatorics of differential operator and very long title, homotopy algebra. Yeah.
Very good. So, as you already said, it is a joint work with Denis Bashkirov, who is my PhD student, and actually everything has already appeared in the Journal of Geometry and Physics. Geometry and Physics. Well, 173 in 2022, and you can find it. You can find the reprint on my homepage. So it's very easily to access it. So can you hear me, the people, online people? Yeah, probably not, but this is all right. Can you read this? No complaints. Yeah, so. Mimo jiné, je tady někdo, kdo nemluví česky? Není, takže já můžu klidně mluvit česky. No, very good. So, yes, I'm going to explain why, or try to give another reason why Lie algebras and similar structures are so omnipresent in mathematics and mathematical physics. And I will start with something very classical, recalling the notion of differential operators or higher order derivations. And then I'll kind of mention some structures relevant to mathematical physics. And in the second part of my talk, or maybe towards the end of my talk, I will also give some general framework in which to understand my calculations. I have to say that the framework will be based on the language of operads, and unfortunately I don't have time during this talk to somehow recall the most basic notions of the theory. So for those who are not familiar with this language, probably there is no other way than just to ignore the rest of my talk. I also have to say that I'm going practically repeat verbatim the talk which I gave on my seminar. So again, if someone already heard it, this will be just repetition. So let me start by recalling some very, very classical notions. So A will be during my talk commutative, associative, commutative associative algebra over a field K, which would probably be of characteristic 0, and it may or may not have unit. I will usually assume that it has unit because it would simplify some things. So everyone knows what a derivation is. So delta or nabla is a derivation if the following thing is true. This is very classical. Well, there are some signs because I assume anything may be graded. Also, nabla needn't be of degree 0, but I'm going to ignore signs if not really necessary in my talk. So if this condition is satisfied, all right? So let me kind of generalize it to higher degrees by introducing deviations. Deviations phi nabla A is a function of one argument from A, and it's defined to be just nabla A. Phi nabla, so this is phi1, phi2, nabla a b is defined to be nabla a b minus a nabla b minus nabla a times b. So you can see some resemblance already. And phi3 nabla a b c. So now it is a function of 3 arguments, is defined to be nabla a b c minus nabla a b c minus nabla a c b minus, again, I said there are some signs which I'm ignoring. So what I'm written will be true if everything is concentrated in degree 0. So what is the term which I am, so this is of course not true, nabla a c b minus nabla b c a and plus nabla a b c plus nabla b a c plus nabla c a b. Unfortunately, there will be some explicit formulas in my talk, and so on and so on. So you can probably already see the pattern in my definitions. And definition, I say that nabla is of order R if phi r plus 1 nabla is identically 0. Okay, so this is I would say of higher order derivation. Definition of differential operator is slightly different, as can be expected from differential operators, and I will recall it in a minute. So notice that derivation of degree 0 is just 0, trivial function. Yeah. Oh, hello. Derivation of order 1 is just ordinary derivation, because vanishing of phi2 means that, okay, this vanishes, which is precisely this equation, and so on and so on.
So that is your definition of something like a Martin and the bialgebras.
Yeah, this is very classical. This is not my definition. Actually, these functions or deviations are also known from statistic. They call it somehow like cumulants, or I don't know how they showed up in many places in mathematics. Yeah, you can, for instance, easily verify it that if phi s vanishes, then phi r vanishes for all r which are greater than s. Therefore, you have a filtration of linear functions like derivations of order 0 of a. Well, this is trivial space. They are subspace of derivations of order 1, and they are subspace of derivation of order 2 of a, and so on and so on. So if you wish to see some examples,
Yes.
then of course the derivation of order 1 is what we would expect, namely if a is polynomial ring in some variables not important here, then something like summation alpha I, where alpha i's are coefficients from ground field, di delta I over delta xi is derivation of order 1, usual derivation. If you want to see derivation of order 2, then you can do something like you can add something like beta ij, again constants from ground field, d squared d xi d xj. Okay, so this is example in summation you can, right? Fine, very good. So this is derivation, and this is example of higher order derivation. This is including this second summand. It is derivation of order 2. As one mentioned, there is also notion of differential operator, which usually is attributed to Grothendieck, but probably he was not the only one who used it. It's defined inductively. Okay, so I'm going to, by the way, can you see it on the board? Yeah. Yeah. Yeah.
Yeah. Yes, I see. Okay, I think I see.
Can you read it? It's readable. Very good. So I'm going to recall the notion of differential operator of order R of A. Again, A is commutative associative algebra. It is defined inductively, namely differential operators of order 0 are just left multiplications. So are linear function that send A to some, let's say, x times A. Let me denote this function by Lx. So this is diff 0, and diff R is a set of all linear maps nabla such that commutator of nabla with this operator of left multiplication is from diff R minus 1 of A. So as I say, this is a definition due to or attributed to Grothendieck. Again, there are some deviations you can formulate. You can find out some deviations which are actually given in this paper also, and I believe it is also very classical. So you can get similar inductive formula, which is not important for my talk. And if you wish to see the example, then each derivation of order R is also differential operator of order R. And if you wish to see example of function which is not a derivation of order R, which is not a, okay, derivation of order R, but which is differential operator of order R, you can add multiplication by left multiplication. So because right.
So is it you only define the degree R is the integer, right? Yeah. But because the differential operator, you can use the Fourier transformation and define.
Well, in functional analysis, you can do various tricks, but I am algebraist. I don't believe in functional analysis. Very good. So this is just recalling very standard things. So do you think that you can switch to this board? So some properties. I'll formulate everything for derivations, but the analogous results are true also for differential operators. But just to save my breath, I'll do it. Yeah. Yeah. Any question?
May I ask a question?
No.
Oh, okay.
Okay, go ahead. I mean, this was the joke. So what is the question?
Do you have an example of a differential operator which is not a deviation, which is less trivial than what was written before? So just you said that.
No.
So differential operator with zero constant coefficient, right? With zero constant term, which is not a deviation.
Well, if A is unital, if A happens to be unital, then indeed the only difference between differential operators and derivations are in this term. Yeah. So they just differ by multiplication, by less multiplication. So they are practically the same. And if A is not unital, well, I'm sure I will be able to cook up an example by all means, but it is not.
But is it possible? Is it possible to find more examples in your paper, which you mentioned?
In a sense, yes. In a sense, yes, because yeah, not explicitly, but the differential operator on free algebras are given by the restrictions on a set of generators of some order. So using this, you can construct the differential operators on free algebras. Beyond these examples, I admit I don't know.
Free commutative algebras. So.
Free commutative algebras,
okay.
Yeah.
Mm-hmm.
Okay, I didn't want to mention it, but
okay.
I'll mention it later in my talk.
Mm-hmm.
Okay, this theorem. That's it. Very good. So what about some properties? As I say, I'll formulate it for derivations, but for differential operators, the statements are similar. So what are the properties? Properties. If omega is from derivations of order S, A, I will probably drop A to make everything shorter, and delta or nabla, what nabla is from derivation of order T, then the commutator omega nabla is derivation of order T plus 1 minus 1. So notice that the particle case is something which certainly everyone knows quite well, that if you take a commutator of ordinary derivation, you'll get again derivation, which has, okay, I will take liberty to write explicitly what I mean by this. This is omega composed with nabla minus, and now you have, this will probably be the only place where I put explicit degree in. So this is degree of omega, degree of nabla times nabla times composed with omega. So notice in particular that if delta is usual derivation of order 1 of A of degree 1, then delta commutator with delta, you will get plus here because of degree is 2 delta squared. And by this theorem, or this observation, this is not a theorem actually, delta square is again derivation. This is very important, very, very important. Yes. Even I can just slightly generalize it, put in S here, and then I'll have something like 2S minus 1. So this is very, very important, and you will see in a minute why I wanted to emphasize so. So this is one property, and the second property is again, well, it's probably not so known, but under the same assumption, the composition of omega with nabla is derivation of order R plus S of A. Yeah, so as an exercise, you may try to prove that.
So the last thing, what is the how to say, composition of the two derivatives?
Yeah. If you have derivation of order S and another derivation of order T, the composition is, oh yeah. So S plus it was T. Thank you. Yeah.
Oh, yeah.
This is a theorem, and just exercise. If you take theta, just ordinary derivation, then theta squared, okay, of degree 0, then theta square is derivation of order 2, meaning that it is annihilated by this phi3. It's just simple.
So in particular, for example, R is the algebra of differential form. Then you also have the same thing, right? R, for example. And because I have to say, before that I know only about the graded commutator bracket. And now you have I didn't know that the second property also holds. Is that a lot of structures? Yeah.
So it is of degree 0.
Yeah, because if it is of degree 1, it will be actually of just ordinary derivation.
But you want it to be odd. I mean, the way I see it for composition is at the degrees. So,
Sorry, I don't get the what is the problem? Degree is not order. Degree is degree like in graded sense. So it's grade. Maybe I had to say grade. Yeah, sorry. I mean, this is just degree 0 map, which happens to be ordinary derivation, meaning derivation of order 1. Yeah. It's just
so the algebra is graded supercommutative, right?
Excuse me?
The algebra is graded supercommutative, if I understand correctly.
Yes, graded if you like
and supercommutative.
Super, if you like super, then it is supercommutative.
Otherwise, no signs.
They are signs there. They are signs. Yeah, but I don't mention signs. I just suppress signs, so they can always be filled in if you are. Yeah. Say it again. Yeah, because you have the what is yeah.
if it is odd.
Oh yeah. I know this. Yeah. There are so many. It is the afternoon and the brain.
In many cases, it has a 0 bracket. Yeah.
Yeah. So the brain is not working in the afternoon, at least not mine. Anyway, so let me finish this introductory part by mentioning a proposition. So if Sx, this is my aim actually now, in a particular case where A is a free polynomial algebra, maybe several, they may not be just finite number of generators, then nabla, a derivation of order R on Sx is determined by its restriction on what? So on S plus. I'll explain what I mean. So this is the direct sum of Si x, where I goes from 1 to n, and Si is a subspace of this spanned by products of precisely I elements. Okay.
Is that a polynomial of degree less than of degree I? Yes.
Yeah, of degree I. Yeah. So not only that it is determined, but if someone gives me linear map from the subspace into S, I can uniquely extend it to derivation of order R. So again. Yeah. Thank you. Of course. And if I replace there by diff, then I shall remove plus here and allow to have S0, which is span of the unit of free algebra. So again, the difference on free algebras is precisely that if I wish to study differential operators, I need also to specify the value on a unit, which in case of derivations is always trivial. Very good. So any questions so far?
But it turned out that this is just unit of differential operators, right? That's what you said.
Say it again.
Because if it's closed under the multiplication, then it contains everything which is generated by vector fields, right? By derivations.
Yeah,
for the free algebra, these are just unit of differential operators, right? That's what you said.
Yeah.
Okay.
Yeah.
And
I think
it might be different in the case of some more complicated algebras, right?
Yeah.
Okay.
Definitely.
Okay, thank you.
My knowledge in this direction doesn't go beyond free algebras. And you will see that even this class contains a lot of interesting examples. So I'm sorry, I cannot tell you more about it. So can we move to this board, Igor? So let me give you one example. Something which is called commutative. Batalin-Wilkowski infinity algebra. Something which mathematical physicists enjoy. So what is it? A is as before graded commutative associative algebra, and okay, nabla is now delta, is of order the degree. So not order, degree, typically plus or minus 1. And I require that delta is the following form, is a summation of things like nabla n h n minus 1, where h is a formal variable, namely something which starts from delta 1, then goes delta 2, h squared, h plus, okay, one more term, delta 3, h squared, and so on. And this is a differential operator of order 1. This is of order 2. This is of order 3, and so on. So this is commutative Batalin-Wilkowski. Oh, maybe I can write it infinity algebra. So, but I wish to emphasize, underline the following thing. If you care to expand d square is 0, which is the axiom, you will get that this delta square has the following expression. So there is delta 1, this delta 1 squared, plus commutator of delta 1, delta 2, h, plus one more term, delta 1, delta 3, plus delta 2 squared, h squared, and so on. So once again, I have delta of this form. I assume that delta squares to 0, which is the axiom of commutative BV infinity algebras. And I expand the axiom, I will get this condition or this equation. This must vanish. And I realize using the properties which I explained before that this is differential operator of order 1 because it is of odd degree. This is differential operator of order 2. This is differential operator of order 3. Therefore, the axiom is of the same form as the defining operation, which is surprisingly deep and important fact. Maybe looks as a triviality, but actually in this case it's kind of triviality, but let's move to something which is less trivial. Yeah, this over there. So now I just wish to generalize the yoga of differential operators to multilinear case. So now I am thinking about maps O from n to the power of A into A. And I say that such a thing is of multi-order I1, In if theta x1 xn is a differential operator of order I s in xs. Also, I believe that meaning is clear. Because for I pick some xs and consider the remaining things constant, and this will be a linear map from A to A, and I require it to be differential operator of order is. Yes. Okay. Yeah, I may also say that instead of multi-order, because this is too long a word, I may say it's of type. I will be probably mixing these two names. Very good. So now the core example of my presentation. This is again just observation, but I am not sure if anyone has made it explicit any place. I consider anti-symmetric bilinear map. I should think of it as of Jacobi bracket, and I recall what the Jacobiator is. So Jac A, B, C is, well, everyone knows what is it. It is I'll write it in this form, ABC plus BCA plus CAB. Now I'm happy in the non-graded case. And of course, I say that this is a Lie bracket if the Jacobian vanishes, as everyone may expect. And then hey, here is the observation. Here is the observation. If the bracket is of type 1, 1. So once again, it means that it is of no just.
Sorry, so this bracket and another bracket has nothing to do, right? Because
No.
because the certainly here G Lie algebra. Yes, so it may
So it is just another anti-symmetric operation. And the observation is that if it is of type 1, 1, then the Jacobian, which is mapped from A tensor 3 into A, is of type 1, 1, 1. And I'm going to prove it. I'm brave enough to try to prove it.
You assume some yes, bracket like that, and
In other words, if bracket is a derivation, ordinary derivation, if in each of its variables, then the Jacobiator is also ordinary derivation in each of its variables. Yeah. So let me prove it. And this simple observation actually started everything. So I will write Jacobiator in slightly different form. So yes, I'm here. A, B, C, namely S, A, B, C plus B, C, A minus C, B, A. I use the anti-symmetry. So this is the last term. Fine. And now I realize that this is minus a joint action of B, C on A. Well, this is not very clear what I mean, but in pictures, this is doing what? So I multiply BC and then I multiply the result with A. So it is, since the bracket is differential operator of order 1 in each variable, this is a differential operator of order 1 in A, the first term. Okay, now what about the second? Now I have to consider these two terms together and write it as a joint action of B commutated with a joint action of C applied on A. So why it is so? Because okay, let's do adjoin C on A. So this is this, and then adjoint action of B. This is the first term. And if I do adjoint B, adjoint C on A, I'll get the second term. And each of these fellows are differential operators of order 1 in A. So I see commutator, so it is again differential operator of order 1. So notice that if I wish to figure out what are the orders in the remaining two variables, then this is the multi-degree of this fellow, and this is the multi-degree of this fellow. I don't have any kind of reduction of orders for C and B in these in the way I wrote it. But anyway, since it is cyclically symmetric, if it is of a differential operator of order 1 in A, it is differential operator of order 1 in any of its variables. So for instance, if I wish to start from beginning and prove that it is differential operator of degree 1 in B, I would need to use different decomposition. So there is something non-trivial going on, and I believe that this is the most interesting point of my talk. So, as usual, trivial things are most interesting. So once again, what I got, that if I have a Lie bracket whose which is derivation, ordinate derivation in each of its variables, then the Jacobi identity is also ordinary derivation in each variable. Let's try to compare it with something different. Now, suppose that I am given, well, just a bialinear operation of A, and I consider associator A, B, C, which is B, C minus A star, B star, C, and I wish to figure out whether the similar thing may be true also for associative algebras. Namely, I assume that it's of type one. So what is type of these fellows? So the type of this is 1, 2, 2. Yeah, why it is so? Because what I have here, I have A, B, C. So in A, it is of type 1. This is clear. In B, it is of type, okay. So here I get type 1 or degree 1, sorry, order 1. And then I compose it with the adjoint action of A, which is another operator of order 1. So I get order 2 in B and similarly order 2 in C. And this fellow is of type 2, 2, 1. Therefore, the entire thing is of order 2, 2, 2, which is the expected value of order of structures with quadratic relations. So there is something indeed quite, well, actually quite deep, quite simple, but quite deep, which is going on in Lie case. No other miracles. Well. So now I have some operads stuff, but as I say, I'll probably skip it and give you some examples instead. Why it is so important and why people kind of use it all the time without realizing what is this justification of computation they do. So the big bracket, big bracket. Big bracket was introduced by Lecomte and Rogers, but it is usually and wrongly attributed to Kozman, Schwarzbach, which is another illustration of the principle that things are never called by inventors, but by someone who reinvented it. So what is it? Again, I promise that I'm going to suppress signs and degrees. So the simplified version without signs is that I take X to be some vector space V, created vector space, plus its dual. And then I definitely have, in that case, I definitely have natural bilinear operation from X times X into symmetric algebra. I recall that Sx denotes the free algebra. And how it is defined? It's defined by alpha u is alpha evaluated at u if alpha is from V star and u is from V, which is also modulo signs, which I didn't mention, alpha, and V is V star is 0. So it is given by natural pairing. And the theorem, which again is a kind of observation if you have in mind all the facts that I mentioned above. Theorem okay, how to formulate it in some simple way. I denote in this way. So I denote in this way extension of this bracket or this multilinear map, bilinear map, as a derivation in each variable. Due to the theorem which I mentioned at the beginning, there exists a unique such a extension. So I can. I can, but no, yeah, V is K vector space. Okay, maybe it's good idea to. Maybe it's indeed good idea to write the extension at least to indicate how it looks. Yeah, this will explain. This will explain. Yes. So very good. So what is? Okay, I have some x1 up to xa. These are generators, and I'm going to give you y b. All right, and this is summation, and the summation Okay, I take product of all x's, product of all y's, B, where here I leave out xi, here I leave out yj, but I put them here. Yeah, and so this is the formula. This is the explicit formula.
Your theorem is the basis.
Excuse me?
What theorem in your
No. This is like 40 years old, or yeah.
The bracket is the beginning, the bracket goes only into
Yeah, but so fine. So this is in K, but this is in Sx. So yeah. Antisymmetric, yeah. Well, and how to verify that the extension is indeed a Lie bracket? So you can struggle with this formula, but you can also observe that actually Jacobi identity is satisfied on X, on generators, and due to this theorem, it's enough. So it is like two lines calculation if you have this theorem. And so why it is so important? Because the standards theorem says that Maurer-Cartan elements in Sx so Maurer-Cartan elements are precisely Lie infinity bialgebras. And there are some particular cases which are important for classical mechanics, I would say, like symplectic, because this is more or less symplectic structure on cotangent space of V or something like this. Yeah.
I do not understand that
If you have any Lie algebra L, which may or may not have differential, that Maurer-Cartan elements are solutions of the equation x dx plus 1/2 xx is 0. Yeah. And there is a principle that each reasonable deformation problem has some Lie algebra such that it is described. Yeah. Okay, so this is but
So the solutions are going to be these polynomials in space X. It's a collections of multilinear maps, and you interpret this multilinear maps as right.
Yeah. Again, I can. This is everything is very explicit. If you give me another 1 or 2 hours, I can expand it into formulas and explain why it is so. But I don't think that you are so excited about it. But anyway, let me. So this was kind of simple, but now I'm coming to something which was not so simple. Meaning that without some deeper insight, you would need to work hard to verify the statement which I'm going to write down. So now I am, we are improving. So now this was a big bracket. Now I am introducing super big bracket. So x, again, for forgetting signs and degree was the same as before. But then I have, again, a natural pairing from Snx time Snx into k. So this is natural pairing. Natural pairing, and which I denote by bracket n. And then I take collection, well, this will be two braces, but the first one, the outmost one is just denoting collection. So h is again formal variable, and I extend it, I still, yeah, I still have it here. I extend it to, okay, 1, 2, 3, which is of the form 1, 2, 3, 1. This one plus two, and so on, such that this is a differential operator of degree 1 in both variables. This is differential operator of degree 2 in both variables, and so on. And again, due to the theorem which I had before, I can very easily verify that this extension satisfied a Jacobi identity by looking at actually in this case product of generators. And why this thing is interesting, because it controls, again, via Malver-Cattan elements, controls deformations of IBL algebras. So IBL is the abbreviation from Lie bialgebras. And this is a structure which people fussing about closed string field theory like very much. Yeah. Okay, so I'm running out of my time. So let me just make a couple of final remarks.
So you are not going to explain the last formula, the last statement, that it controls the formations of.
No. This is just this is not the subject of my talk. Again,
Okay.
If you give me another maybe 2 hours, I can explain.
I can, but the others probably can't.
Yeah. So by the way, well, I don't think it's appropriate to run over time, but I can give you some reference for this result if you want, if I am able to find it. Where is it? It is in the paper of Campos, Merkulov, and Wilbacher. So if you search at archive for these three names, you'll get very easily hold of this paper, which is like 70 pages long, as all papers in this area. Yeah, it is cited. Yeah, you did good point. There is a precise citation also for this result. Yeah. So fine. So final remarks. Commutative associative algebras. Algebras, just associative. And the algebras. So this is a triple, which was called, I think, in a very appropriate way, three graces by Lode. And the main, let's say, the main statement of our paper with Dennis, or one of the main statements, says that only this has this property. We call this type of algebras tight. So very roughly speaking, tight means that if the operations of a given algebra are derivation of degree 1 or degree S in general, then the axioms are of the same type. And out of these three graces, only Lie algebras have this property.
Which property?
Precisely being tight, namely, yeah, like Jacobi identity is of type 1, 1, 1 if bracket is of type 1, 1. It is not true for associative. Yeah, actually the statement is much more general there, that the only operations with one quadratic operation and one quadratic axioms, which is tight in this sense, is Lie. And actually also Lie infinity, if you know what is it. So you have many things. You have differential, and this IBL in infinity, which I mentioned, was it this commutative battle in Wilkowski, which is still here. It is actually L infinity, where only differential is non-trivial, so it also fits into this scheme. And let me end by a bit of philosophizing. So why commutative associative algebras are important, why we can see them in nature. Yeah, because many things, natural things like natural numbers, multiplication and addition are commutative. All bookkeeping calculus is based on commutative things. So there is a nice justification why commutative associative algebras are important. Well, associative algebras, why? Because group of transformations are associative. So my favorite, but not commutative. I won't be able to reproduce it, but if you do it like this, you can very easily demonstrate by yourself that O3 is not commutative. But why Lie algebras? So of course, why one may say that Lie algebras are infinitesimal versions of groups, of Lie groups, but where is infinitesimal calculus in nature? I don't know. This may give another justification why this so. I have some other justification, but it would go beyond this talk. Like this is causal dual to this one. This is causal self-dual, but it would go beyond of what I was able to tell you in my time. Okay, thank you very much.
Thank you. Martin, I have very kind of apply question, because I also see some a lot of geometric structure related to homotopy, algebra, and IBN. I see in some work. And can you compute some invariant of them, like cohomology and Fan-Fuchs cohomology?
I never did any useful and explicit calculations.
You don't know the explicit calculation method, only general theorem.
I only explain things. I don't calculate.
Yeah. Okay.
So like maybe at the beginning of my career, I calculated something, but otherwise
Then,
I'm just
yeah,
explaining.
Yeah. Okay. So is there more some questions? No. If there are no more questions, then okay. Then so then if you don't have any calculation, how you consider on the structure viewpoint, need to finally to understand how to they are really different structures. Then you have to calculate something, or it's a calculation you can still say that the thing are different.
I don't know what to say.
Okay. Then yes. Then thank you. Yeah.
Yeah. Okay.
Can we ask?
Sure.
Example of the duality of the algebras and this commutative associative ones.
Yeah.
Example going behind beyond numbers or beyond something at least.
Yeah. So I mean, I can formulate it in terms of operads, but I can also formulate it in kind of classical terms. So the Lie algebra on some vector space L. Again, I'm suppressing signs and degrees. So V, not L. So Lie algebra is the same as so what is this? This is co-free, co-nilpotent, co-associative, co-commutative, no, on V, and this is quadratic coderivation that squares to 0. So this is the same. By the way, this is observation which goes back to founding fathers of rational homotopy theory. So it's like the 70s probably. Sullivan certainly knew it already. And so this is from Lie algebras to commutative associative, and vice versa if you have commutative associative algebra. Associative algebra on W, then it is the same as now you have to take co-free, co-nilpotent Lie algebra on W and quadratic coderivation which squares to 0. This is this is determined. I mean, it's one-to-one correspondence. If you give me bracket, I'll give you a formula. Well, this will be kind of difficult because I would need to work with co-derivation of coalgebras, which is not something which human being like, but I can do it.
But it's due to the normal things, to commutative algebras and derivations, right? You can always imagine and dualize.
They are all, say it again, please.
I mean, co-algebra is due to an algebra. You can just always dualize these structure maps. So it's not hard to imagine.
If you dualize co-algebra, you get algebra. But
yes,
if
right.
you dualize algebra, you don't get co-algebra. There is a dualization between algebras and co-algebras, which are they call it local, which means that the product is continuous in open compact topology. So
okay. So
but in finite dimensional
infinite dimensions, of course, yes.
Yeah, infinite. One has to be careful about it.
Yes, sure. Yes.
Mm-hmm. So of course, then you can forget somehow and just speak about free algebras.
Yes.
Free. Yeah.
So the rule commutative associative invalid
No, not involutive. This is, well, we'll forget co whatever. So commutative associative structure on W is the same as derivation, quadratic derivation on free Lie algebra with squares to 0. Yeah. And vice versa, Lie bracket on V is the same as derivation, quadratic derivation on free commutative associative algebra squares to 0. There are some signs involved, but yeah. So thank you for your question. Actually, I always feel that I wish to talk about something very elementary, which is usually more interesting than the things which I'm doing. So this is classical stuff, but very nice one.
Okay, so let us take this further. Our seminar today, and the next week we have the B3 libraries. Yeah.